In section 14.3, we look at Hamilton paths and Hamilton circuits. In the last section, we studied paths and circuits that covered every edge of a graph. Using every edge of a graph exactly once is helpful for garbage collection, curb sweeping, or snow removal. But what about a UPS driver trying to find the best way to deliver packages around town? We can model the delivery locations as the vertices on a graph and the roads between the locations as the edges. The driver is only concerned with finding a path that passes through each vertex of the graph once. It is not important to use every road or edge between delivery locations. Trying to find the best way to deliver packages around town or planning the best route by which to run a series of errands can be modeled and solved using paths and circuits that pass through each vertex of a graph exactly once. A path that passes through each vertex of a graph exactly once is called a Hamilton path. If a Hamilton path begins and ends at the same vertex and passes through all the other vertices exactly once, it is called a Hamilton circuit. So let's look at the first example. We want to find a Hamilton path for the graph, which means it has to pass through each vertex only once. This graph has a ton of paths that work, but one of the easiest ones is A to B, B to C, C to D, and D to E. I hit every single vertex only once. I didn't need to use the edges because that doesn't matter here. So one Hamilton path would be A to B, B goes to C, C goes to D, and D goes to E. If we wanted to find a Hamilton circuit, which means it has to start and end at the same spot, so we need to finish out at vertex A, all we have to do is then connect E to A, and that will close off the circuit. Again, this graph is going to have many paths and circuits, but this is one of the easiest ones. However, because it has 4 vertices of odd degree, it has no Euler paths and no Euler circuits. When it comes to Hamilton circuits and Euler circuits, a graph can have one or the other, or both, or neither. So they aren't related. If it's Hamilton, that doesn't mean it can't be an Euler. If it's Euler, then it can still be a Hamilton, or it can be neither. There's no relationship between the two. A complete graph is a graph that has an edge between each pair of its vertices. Can you see in the graph above that it is not complete? There is no edge between vertex A and vertex D. Nor is there an edge between vertex B and vertex C. Complete graphs are significant because every complete graph with 3 or more vertices has a Hamilton circuit. The graph below has an edge between each pair of its 4 vertices. Thus, the graph is complete and has a Hamilton circuit. It actually has many Hamilton circuits, one being A, B, C, D, A. Any 2 circuits that pass through the same vertices in the same order will be considered the same. In order to avoid this duplication in forming a Hamilton circuit, we can always assume that it begins at A. There are 6 different or unique Hamilton circuits for the graph above. We have ABCDA, ABDCA, ACBDA, ACDBA, ADBCA, and ADCBA. To build these 6 Hamilton circuits, you'll start at A and form all ordered arrangements of the remaining 3 letters and then return to A. Each of these 6 different Hamilton circuits can be written in 4 different ways. So to find the number of Hamilton circuits in a complete graph, we have a formula. If our complete graph has n vertices, we can plug it into n minus 1 factorial. And what factorial means is we would multiply every number down until 1. So for example, if I plugged in 3 factorial, that means I'm multiplying 3 times 2 times 1. So you just take the number and you multiply it by every number less than it until you hit 1. So let's go ahead and try this with example number 2. We want to determine the Hamilton circuits in a complete graph. The first one is with 4 vertices. So n is equal to 4. So plugging it in, we have 4 minus 1 factorial, but that's 3 factorial, which is 3 times 2 times 1, or we get 6. What about with 5 vertices? This time n is 5. So plugging it in, we have 5 minus 1 factorial, which is 4 factorial. We've got 4 times 3 times 2 times 1. 4 times 3 is 12. 12 times 2 is 24. And 24 times 1 is 24. And 8 vertices. This time n is 8. So when I plug it in, I have 8 minus 1 factorial, which is 7 factorial. That's 7 times 6 times 5 times 4 times 3 times 2 times 1. And when I multiply this all out, I end up with 5,040. Sales directors for large companies are often required to visit regional offices in a number of different cities. How can these visits be scheduled in the cheapest way possible? For example, a sales director who lives in City A is required to fly to regional offices in cities B, C, and D. Other than starting and ending the trip in City A, there are no restrictions as to the order in which the other 3 cities are visited. In the graph below, the vertices represent the cities. The airfare between each pair of cities is shown as a number on the respective edge. A complete graph whose edges have numbers attached to them is called a weighted graph. The numbers shown along the edges of a weighted graph are called the weights of the edges. Our goal is to find the Hamilton circuit with the lowest associated cost. The graph below is a model graph for one-way airfares for cities A, B, C, and D. Use the weighted graph to find the cost of the Hamilton circuit ABDCA. So let's go ahead and just draw out the circuit first. We go to A from A to B, and then we go from B to D. We go from D to C, and then we go C to A. And so we just want to pull the numbers that are on the purple edges. And it doesn't matter which way you add them up because we'll get the same answer regardless. From A to B, we spent $190. From B to D, we spent $155. From D to C, we spent $179. And from C to A, we spent $124. So when I add that all up, the total cost of the trip was $648. The traveling salesperson problem is the problem of finding a Hamilton circuit in a complete weighted graph for which the sum of the weights of the edges is a minimum. Such a Hamilton circuit is called the optimal Hamilton circuit or the optimal solution. One method for finding an optimal Hamilton circuit is called the brute force method. The brute force method of solving the traveling salesperson problem is found using the following steps. First, you will model the problem with a complete weighted graph. You will make a list of all possible Hamilton circuits. You'll determine the sum of the weights of the edges for each of these Hamilton circuits. The Hamilton circuit with the minimum sum of weights is the optimal solution. So let's go ahead and try this with example number 4. The first thing we need to figure out is how many possible Hamilton circuits do we have? Well, we have 4 vertices. So if I plug it into my formula of n minus 1 factorial, I get 3 factorial, which is 3 times 2 times 1. So there are 6 possible Hamilton circuits. And so we need to find all of the possible Hamilton circuits. To find these, the first thing is they're always going to start at A to make our lives easy, and they're going to end at A. What we have to do is write the order of the other 3 vertices and change it up in between those A's. So the first one would just be to do B, C, D. Just write them in order. Then we want to change up the order of B, C, D. Maybe instead of doing B, C, D, we'll do B, D, C. We just changed the D and C around. Well, maybe we don't want to have B first. We want to have C first. So if I have C first, I only can do B and then D. Or we have another option. We could do C first and then do D and B. That takes care of 4 of my 6 possible. But what if I don't want to put C first and I want to put D first? So if I put D first, I have B and C left to choose. Or I can do C and then B. Those are the 6 possible Hamilton circuits. So now that I have these all listed out, I want to find out what the associated cost would be with this circuit. So from A to B, I spent $190. From B to C, I spent $126. From C to D, I spent $179. And from D to A, I spent $157. So the total trip cost me $652. Then we want to do the other paths the same way, and then we want to see what is the smallest amount of money that was found. So A to B is 190. B to D is 155. D to C is 179. And C to A is 124. So this gives me a total cost of $648. A to C is 124. C to B is 126. B to D is 155. And D to A is 157, which gives me a total cost of $562. A to C is 124. C to D is 179. D to B is 155. And B to A is 190. So this gives me a total cost of $648. A to D is 157. D to B is 155. B to C is 126. And C to A is 124, which gives me a total cost of $562. And the last one, A to D is 157. D to C is 179. C to B is 126. And B to A is 190, which gives me a total cost of $652. So now what you want to do is you find the lowest price. And in this case, we actually ended up having a tie of $562. And so what that means is the two optimal paths are A, C, B, D, A, and A, D, B, C, A. Now, as the number of vertices increases, the rapidly increasing number of possible Hamilton circuits makes the brute force method impractical. Unfortunately, mathematicians have not been able to establish another method for solving the traveling salesperson problem, and they do not know whether it is even possible to find such a method. There are, however, a number of methods for finding approximate solutions. So the only way to be sure that it is the most optimal solution is the brute force method. But as you can already see, just even doing those 6 circuits took us a long time, let alone if we were looking at 5,040 of them. Nobody wants to do that by hand. So we have ways of approximating solutions that are pretty good. By continually taking an edge with the smallest weight, we can find the approximate solutions to the traveling salesperson problems, and we call this the nearest neighbor method. So the nearest neighbor method of finding approximate solutions to traveling salesperson problems is used with the following steps. You model the problem with the complete weighted graph. You identify the vertex that serves as the starting point. From the starting point, choose an edge with the smallest weight. You'll move along this edge to the second vertex. From the second vertex, you choose the edge with the smallest weight that does not lead to a vertex that has already been visited. You'll move along the edge to the third vertex. You'll continue building the circuit one vertex at a time by moving along the edge with the smallest weight until all vertices are visited. From the last vertex, you have to return to the starting point. So let's go ahead and try this with example number 5. A sales director who lives in City A is required to fly to regional offices in cities B, C, D, and E. The weighted graph shown gives the one-way airfares. Use the nearest neighbor method to find an approximate solution. What is the total cost? So we know we have to start at A and we have to end at A because that is where he lives. So sitting at A, we want to see what the smallest weight possible is that comes on the edges from A. So we have 128, we have 147, we have 114, and we have 180. So because the smallest weight is 114, we are going to travel down to C. From C, I have to then find whatever the smallest edge is, as long as it doesn't go back to A, because I have to hit all the vertices before I go back to A. So from C, I have 169 as an option, I have 115, and I have 116. So because 115 is the smallest weight, I am traveling to E. From E, I can't travel to A because I still haven't been to B or D. So I need to either pick the 195 or the 194. So since 194 is cheaper, I'm going to travel to D. Now I can't travel back to A just yet because I still haven't hit vertice B. So even though we have all these options of 195, 147, 145, and 169, I have to go to B. And it is the cheapest, so that actually ended up working out nicely, but I have to make sure that I hit all the vertices before I can go back to the starting point. And from B, then I go back to A, because all of my vertices have now been used. So let's go ahead and write down what our circuit was. We went from A to C. From C, we went to E. From E, we went to D. From D, we went to B. And from B, we flew back home to A. So let's see what the total cost of our trip would be. From A to C, we spent $114. From C to E, I spent $115. From E to D, I spent $194. From D to B, I spent $145. And from B to A, I spent $180. Which means that the total cost of my trip is going to cost $748.